Okay, so let's start with the morning session by Phil. I think this is number 5 discussions, or number 4 continues.
Yeah. All right. So I want to finish up. I don't have actually too many slides. And then I wanted to discuss. So why don't I just finish up? So I was talking about long-lived particles. And so I just wanted to recap how you look for them. So one way is that long-lived particles can be heavy. So this is like we start with the neutrino detectors, right? We can use timing information to separate out long-lived particles from other particles. You can certainly just use timing information inside a detector, so you can do it at LHC or another experiment. So you can go fast, right? They're long, they're heavy. Right? If the detector is, the other way is to just look for long-lived decay. So you could go high, or you could go long. The other thing is to kind of put the detectors in a region where there's an intense beam. So, making a beam dump, or putting it in a beam dump, or putting it in, some region with high particle flux. So here's just the phasor for high particle flux. These are all LHC just because there's some nice graphics on it. And then you could also put the experiment and parasitically build it off an existing experiment. So here's the CODEX-B experiment, which is in this small room that's next to the collision point of here's LHCb. This is the LHCb experiment. So the next thing to remember this is 0. This minute. Okay. Yeah. Should I keep going? I mean, is it the speaker?
No, I think it's okay now.
All right.
That one was on.
Oh, okay. All right. So the nice thing to remember is that you can either go fast, go high, go strong, or go together. And this is the same slogan for the Tokyo Olympics. So, faster, higher, stronger, together. I actually wrote this independently, but I had to change together. I wasn't sure. Anyway, so if you want to think about long-lived dark matter, just think about faster, higher, stronger together. So I want to just finish with kind of a few more models that you might be familiar with, and I could have spent whole lectures on, but I really didn't have. At some point you have to choose. So another very common model these days to explain dark matter is a heavy neutral lepton. And there's various incantations of this model, but kind of the simplest one, or the most common one you hear about these days, is to take the left-handed neutrinos and then add a new sterile right-handed neutrino. And then through the seesaw mechanism, you can get light neutrino masses, which you often write as some mixing u squared times some higher mass scale. Now, it turns out that you can get, you can explain baryogenesis, you can explain dark matter. If all of these neutrinos are just the right masses, and typically what this means is you have one that's in the kind of KeV region, and then 2 that are at the GeV region. And I think to get dark matter, these have to be somewhat fine-tuned. So these have to be kind of light in the 2 to 3 GeV region. But the other thing, yeah.
This is kind of a naive question, but is it typical for sterile neutrino models to have 3 sterile neutrinos? I feel like I've mostly heard of there just being 1 sterile neutrino.
So traditionally there was one. I wouldn't say typical is a hard question to answer, but suffice it to say there's a group of very loud people who talk about 3 sterile neutrinos. Like they always. Have you guys seen Billy Madison?
Yeah.
Yeah. So like the O'Doyle rules guys. All right. So let me explain for people who haven't seen. So if you go, there's a Adam Sandler movie from the 90s, and there's a bunch of kids. He has to go through every grade in school in like 2 weeks. And there are a bunch of kids in the corner in every class that are O'Doyle's. And every time he goes in the class, they say O'Doyle rules. So at conferences, you have these people that say right-handed neutrinos rule. And so every time you talk about dark matter. So there's, and I mean, and they've come up with they've worked out a model that kind of explains everything. But yeah, some people like it, some people don't. But it's certainly something we should look for. And so the way, all right, so what you get out of this by having these like neutrinos is a bunch of new interactions, because these right-handed neutrinos can mix with the light neutrinos. And so now you can have a W that can decay to a lepton and a heavy neutral lepton. You can also have a Z decay to a neutrino, a heavy neutral lepton, and a Higgs to neutrino, heavy neutral lepton. And the other thing is that, right, so here are some bounds for the y-axis here is a kind of mixing angle, right, from this matrix. And the x-axis here is dark matter mass, right, in the KAV region. And so there's kind of a region, kind of an, I wouldn't say a tight region, but there are some constraints all around it. And you can, you know, some people are very excited about like a KAV line they see that could explain a light neutrino, but some people have also said they've ruled this out. I don't know what the status is at this point. I know people who have ruled this out, and I know people who say it's still something to believe. Yeah.
What is the L6? Why?
Oh, these?
Yeah.
I think this is for the Lyman alpha. So this, right, this changes the content. I don't actually know the details.
Okay.
Yeah, it has to do with the Lyman alpha bound. So.
Like not lectures on material.
Yeah. Yeah, all right, so these are, yeah, we're gonna have lectures, so you can ask them. I'm sure they're gonna show this a lot. So that's the lightest candidate. Here are the other two heavy candidate bounds, right, from, so these guys are, all these constraints are from various cosmological constraints. And then you actually have a bunch of experiments. So how do we actually look for sterile neutrinos? Well, at the LHC, the classic way is to look for them in W decays. So you just have a normal W production from quarks, and you produce a lepton and a sterile neutrino. And then this sterile neutrino will then decay to a W and a lepton. And the nice thing is that you get two leptons that are same sign. Two same sign leptons at the LHC is a rare occurrence. And you can basically reduce your background by many, many orders of magnitude by looking for two same sign leptons. And then if you add a W, you can put even, looking for that W decay gives you even stronger bonds. And you can look for, people look for W to quarks, they look for W to lepton. It depends on your interest. Both are about equally sensitive. And the leptons is better at low mass, quarks at high mass, and so on. Here's bounds. So these are, I think these are the strongest, most recent LHC bounds. And the idea here, you can see that the bounds are on the order of 10 to the minus 5, 10 to the minus 4. In the small mass region, this thing has a very weak, because of the mixing angle, it's the couplings are suppressed here, right? It's suppressed by like the U squared. And so in the low mass region, these again can be long-lived, right? So you can actually, the strategy here for like a light heavy neutral lepton is to look for long-lived. And given that, you can build another experiment that looks for it. So if your heavy neutral lepton is very light, you can see it in D decays. And then this guy, once it's light, will be quite long-lived. And this long-lived experiment, or heavy neutral lepton will then decay, and you can look for a pi in its decay. And there's all sorts of experiments that are looking for this. And it turns out, right, all the experiments I went through yesterday, can put some constraints on this. So I think this is the most recent set of bounds I could find on the U squared. And so you can see, right, the LHC bounds are at 10 to the minus 5. Here, once we have like a high intensity beam and we look for long-lived signatures, you can actually go even lower, significantly lower. And here are the various bounds. And just to summarize, the takeaway from this plot is that, so I think T2K, like neutrino experiments in general, tend to give pretty good constraints for heavy neutron leptons, as well as the Na62 experiment also gives good constraints. And the Na62, I don't know if you remember, has this big volume. So you can produce particles and then they can live for a while and then decay. And so it turns out it works pretty well.
Sorry, what's pi nu?
Pi nu is, it's actually from Na62. Or I think it's, I think so. It's like the pi nu decay, K to pi nu decay, Na62. Don't quote me on that. I should remember. I can point you to this paper. Yeah. Another question on this?
No.
Okay. Yeah. All right. So now I wanted to talk about the most old school model in all of my lectures, which is the Wiener-Higgsino. This is the only time I will talk about SUSY. I guess, you already had lectures on SUSY. So there is one model that is quite popular these days at the LHC. And it's not the last SUSY model that's alive, but it's the one that I think people talk about the most because it can explain dark matter and we still haven't observed it. And that's the idea of you can get a chargino that's either Wiener or Higgsino-like. For people who are not super familiar with SUSY, that's just a heavy charged particle. And this heavy charged particle that can then decay to a dark matter candidate, neutralino, and a soft pion. And it turns out that you can explain the relic density, you can explain not observing it if you make the mass of the chargino to be very close to the mass of the neutralino. So you have a very narrow mass splitting. So in the MeV range, right? So they're very, you could say fine-tuned. And the nice thing though is that this will give the chargino will have a lifetime. So it will live for a while and then it will decay. And so what this does then is that this gives you a charged particle that then disappears. Yeah.
So I know people at the LHC are kind of sad about SUSY, but with this kind of model, is there a full supersymmetric sector that is still viable?
Yeah, at a higher scale. Yeah.
Okay, so it's just existing at a higher energy.
That's right. So this would be your lightest, or sorry, your neutralino would be the lightest particle in this scheme.
So was there a reason to suspect that SUSY was going to exist at a scale, like at that lower scale? Like, I guess what I'm trying to ask is like, why are people kind of depressed about it?
They thought that the Wimp miracle scale was the scale of SUSY.
Okay.
So, and then, you can always, it seems you can always push SUSY to higher scales, but you actually have to start kind of tuning things, right?
Okay.
And that's why people have gotten depressed, because there's a scale where you can SUSY still can live forever, right? But there's, it gets kind of stretched. I think that's as much as I'll say. I'm no expert on SUSY, so you can ask somebody older, and they'll tell you.
But these aren't web scale particles that we're talking about. These dark matter things.
No, so so if this is typically, so here's actually the relic density this is for the Wiener-like version of this, and you have for a neutralino mass of about 3 TeV, you can get the right relic density.
Gotcha. Okay, thanks.
So the chargino has to be on the order of 3 TeV if it's Wiener-like and like 1 TeV if it's Higgsino. So okay. So practically speaking, what does this mean? It means you get events like this. So you have a collision here, and then you have a charge going through, and it looks like a charge, it's just a charge track. And so you'll have hits in your detectors if you can measure charged particles, and then it decays and then it disappears. So the fun thing is that you have to do a special reconstruction. It's a special decay mode, and it's a very striking signature because there's no standard model particle that will do such a thing. And yeah, there's like lots of handles you can use. So this turns out to be one of the best bounds and kind of the last surviving, one of the last surviving. So now I want to just, so last lecture I was talking a little bit about the dark sector, but you can make the dark sector very complicated if you want. And I'm sure Josh talked about SIMS. So the idea here is that, well, we have a bunch of new dark particles, we could call them dark pions. And you can play around with the cosmic history of dark pions. For example, if you have 3 to 2 processes, right? So the case where, I don't know if Josh calls it cannibal dark matter anymore, but the case where the dark matter candidates can eat a dark matter. So when you're thermalizing, you get this process. And I won't talk about the details of the cosmic history, but it suffices it to say it's interesting. But the other thing this gives you is kind of a rich dark sector, and that the rich dark sector gives you lots of like new and interesting handles to look for. And the other thing is to kind of get this to work, you have to couple these to some sort of portal mediator. So typically people add a dark photon. You can add other portal mediators as well. And this gives you a coupling, and this gives you a mass. And so basically, like every other plot I've shown you, we can get some sort of epsilon coupling and mass coupling, and you can get bounds. So these are all the different cosmic bounds and direct detection bounds and indirect detection bounds. And suffice it to say, you need a small coupling, and you need a light dark matter candidate. That at least that's a good model for this. And the small coupling will give you long-lived signatures, right? The dark matter will give you light dark matter. And so then you can imagine using one of your existing light dark matter examples to look for these decays. So what do they look like? Well, you can have a dark vector meson, V. And if we give this a portal mediator that's like a dark photon, then you have like all your dark photon bounds survive, at least assuming this model. So you can have a dark vector meson decay to a dark photon to leptons. And then you can imagine taking your experiment, like a beamed up experiment, firing it on a target. So you could take an electron or a proton on a target. And then you can look for kind of fun final states where you have this guy decays to a dark photon that then decays to a dark charged vector meson that also decays to a dark charged pion. This maybe is your dark matter candidate. And this dark charged vector meson then decays to another dark photon. And then you get leptons and another dark pion. So something rather complicated, but what we would observe, right? These guys are dark. So we would observe just leptons, a dark photon decaying to leptons. Right, so, and since these couplings, the couplings to the standard model are weak, this would be displaced, yeah?
So is this a case in which you would be looking for missing PT?
So this would be, yeah, so if you had LDMX, you could look for a missing transverse momentum, that's right. It's often the case that this dark photon is long-lived. So you could look at this with the long-lived experiments like Darkwest, or you could look at this with HB, heavy photon surge. All of these experiments have some ability to constrain this.
Got it, thanks.
Question in the back?
So now that you mentioned all these experiments, but I would believe that these models are pretty rolled out because of the dilepton side that they have.
So this coupling is super weak, and so the rate of dileptons is actually quite low. So
okay.
yeah. So this is, it's like all the other dark photon models, that you have this epsilon mixing coupling, and basically it's like a dark photon analysis, except now you have this rich dark sector, so you can get other missing energy decays. So the other thing you can have, right, is that these decays, this takes enough energy that you get really low energy electrons, right? And these just kind of vanish, right? So, yeah, so I mean, just to get you even more excited, this would be a charged vector meson, but you could also have a neutral vector meson decay, right? So you could have a dark photon to a neutral vector meson that then decays to a neutral dark pion, and then you get leptons. So again, this would be leptons plus some invisible signature, but right, the final state would be a little different. So, I mean, once you make your dark sector kind of rich and interesting, you can get all sorts of kind of fun things. Practically speaking, what we're seeing in the end is a signature that's the same, right? Leptons are the same, but then you have all sorts of other missing energy signatures that are coming in. And just to extrapolate this idea to like very high energy collisions, you can imagine at the LHC, these dark sector things showering. So you can imagine, let's say you have a heavy vector meson. Sorry, let's say you have a heavy spin 1 mediator, like a Z prime. This diagram I stole, it has an A prime. So imagine you have this heavy vector mediator, then decays to dark quarks. And then you have a dark shower into dark pions and dark rhoes. And then these dark pions and dark rhoes then actually decay to regular quarks. And so you have jets or even pieces of jets that start to appear in here. And actually some people call these, they say they emerge out of nowhere, right? So kind of one, at least word for these is emerging jets. There was a nice paper on this. And these, the fun thing is that you can get all sorts of crazy decays here. And just to give you an idea of what this might look like, so here's a nice photo of this. So these are the like emerging jets. So you have a collision here. This is CMS, and then you have kind of particles that appear, right? Like, so this would be a di-emerging jet event. So you have particles that kind of appear in the middle of the vector. So this would give you a big cluster of long-lived particles. You could also imagine like prompt and long-lived particles. You could also imagine like part of your jet is just missing. So it's some combination of missing energy, long-lived particles, and regular particles. So things will just look different. And so any way to make this look different is kind of could be an explanation for a rich dark sector. Yeah, and then here's kind of the conventional searches for, so if we just take these bounds, right, these target bounds for like a low mass synth. So this would be the mass of your dark photon in a synth model, and this would be your coupling. And so here you can see all these experiments playing a role. So like the heavy photon search, LDMX, Sequest, the invisible LDMX search, here's Bell 2. So all of these light experiments can play a role. And so, this guy's looking for like a displaced dark photon. This one is doing the monophoton analysis. This is the LDMX invisible. So you can see each one play a role. And you can see that we're kind of in the interesting phase space too. Yeah?
Yeah, so
I think some people, I can't remember who's looking on this, but I think some people are looking for dark jets and showers from like cosmic rays.
Yeah.
So how does it, and then they will have some line, right? So how would that light appear in this plot? Do they probe a different space or?
Yeah, that's it. Okay, so no, it would probe the same space. So it depends on your detector, right? The line sensitivity. So the idea would be, let's just draw this out. This is a good kind of. So you have a shower of dark pions. So let's say it's dark pions or dark vector mesons, right? And then this guy showers. And then eventually, in one of these showers, you're gonna get a dark photon, right? And then this thing will decay to like electrons. So now a normal shower, cosmic shower, would be like a proton, and you're just gonna get like a similar, sorry, you'll get like some quarks and gluons and quarks and gluons. And then eventually you'll get right, some sort of mesons, so maybe some pi naughts. So your composition, this will be filled with electrons, and if this is very light, you'll have a very high electromagnetic content. Whereas this guy, this can decay to right, muons, so you can get like muons and electrons and yeah, mostly this will be muons and electrons. And so this will, oh, and photons, lots of photons. And so then this will have like a high, large number of electrons, whereas this will have more muons, more photons, right? And so the shape of the shower will be different. The composition will be quite different. And so what you can do is you can, these days there's a lot of detectors, right? These ground detectors, they can actually separate electrons from muons by looking at Cherenkov radiation, for example, and scintillation. And so you can actually measure the electromagnetic content or even the electron content, right? And you can separate this guy from this guy. And then the bounds that you would get on this, right, are just the bounds on like how these guys would be produced. So you could actually take, you measure like 1 million showers like this, and you can measure the electromagnetic content, and then you can translate this to a bound here. So, right.
So how do they appear on this plot? How
Wait.
Yeah, so after you do all that, and then you get one line on this plot, how does it look like? Like how competitive are all these like cosmic ray
So,
experiments?
Yeah, so my guess, all right, the usual rule with cosmic ray experiments is that in this region, it probably you won't see it, right? Mostly because epsilon cosmic rays are, it's not like a beam where you get 50 million interactions per second. Cosmics, you get, a few per second if you're lucky. So this epsilon will be very high up here for a light dark photon.
Oh,
But-
very high. Because I was thinking like, like universe is a huge as collider, right? So you can put like higher energies now and would
Exactly. So I was getting there, right? So it's very light here when the dark photon is light. When the dark photon is super heavy over here, the cosmic are basically the only bounds you can get.
Oh,
So and then the bounds are going to be probably still very high, but they're going to be better than everybody else. So yeah, like in the TeV region, cosmics can start to take over in terms of bounds.
okay, cool. Thank you.
Yeah.
So I probably missed something very elementary, but why wouldn't the dark photon also decay into muons?
Oh, this is if the dark photon is light, right? So I was trying to come up with an example. I mean, I'm trying to think off the top of my head, but yeah, in principle, dark photon can decay to muons too if it's heavy enough. The composition will be different, right? Because you'll have a lot of neutrinos in these decays, right? But this will have dark pines. I mean, you'd have to think about exactly the differences. So I haven't done this actually exercise before. So.
Thank you.
What was your question about this?
It's about that plot.
Go ahead.
What is Sequest? What is that experiment doing?
Oh, Dark Quest? Sequest?
Sequest, yeah.
Sequest, this is actually, now we call it Dark Quest. So, but yeah, Sequest, it's a, yeah. Sequest is the one I can like talk endlessly about.
The one who was soliciting the full logo.
Yeah,
Oh.
Lighthouse.
yeah. Yeah, we made this lighthouse logo. It was nice. So this is Sequest. So we call it Dark Quest, right? So it's protons on a target. This target is, oh yeah, didn't even have to look. This is a 1.8 Tesla magnet. And so protons come in, the magnet sweeps out particles. And so this is a 4.9 meter beam dump. And so your beam dump basically absorbs everything. And then you look for particles on this other side of the beam dome. And so you have a bunch of muon chambers at the moment and a magnet. And then the plan is to put an electromagnetic field in it. So,
And it does such a good job of excluding perimeter space because you have directional information?
so the reason it's so good is that this beam dump is really small. And there's a magnet, so you can make it really small. So it turns out that the best lifetimes for these values of epsilon is on the order of like 1 meter, right? So when things are a little boosted, this setup is really good at removing everything and just giving you one.
Got it, cool, thanks.
So I have a question on the, when we were talking about before.
Yeah.
These displaced jets. So I think this is for this soup that we were talking about yesterday, right? So when we were talking after class, you said that this soup is kind of hard to look for at the IHC. But something like a displaced jet like this, I mean, isn't that a striking signal?
Yeah, so this is not a soup. But yeah, this is a very striking signal, and you can do a nice like displaced jet search. Yeah, the soup, it's more complicated. The soup is so I'll get to the soup in a sec. So maybe let me just keep going. So you can have an even more complicated, yeah.
There's one more thing.
Oh, there's one more question? Yeah, I can stay here. The next slide is soups, right? Okay, so.
So this is just, it's a more general question, but I wonder if it would make sense to like perform these collider searches also like on heavy ion collision runs, or like just the combinatorial background would make it hopeless.
No, so there's certain dark searches that are way more powerful in heavy ion collisions than regular collisions. Yeah, this is a great question, and I was gonna put some slides on why heavy ion collisions are actually more powerful. So why don't I just, since this is a discussion, let me just do this for a second. So you can imagine having like a lead ion, so Z is something large, right? It's 82 or something. And then you have another lead ion, right? And they're going by each other. So one nice thing is that you can have a peripheral collision, and then you can imagine, since these guys have like huge charge, you can have them interact with photons. And so you can have them, for example, an ALP. So you can have a pseudoscalar. I'm gonna write it like this. And then this will decay to photons. And it turns out that at least for some region of phase space, this bound, so this is an axion-like particle. It turns out for a large region of phase space, this lead scatter bound is the strongest bound. And so heavy ion collisions, the nice thing is since their charge is so large, right, you can get processes that are coupled to photons, you can get huge enhancements. Right, this is going to be, right, this vertex is going to be Z squared dependent. Right? So you're going to have a huge enhancement of like 82 squared in your cross section.
Makes sense.
Yeah, but it's actually there's a lot of interesting things you can do, and you can imagine like a heavy iron on the target, for example. There are a lot of things you can play around with. Typically, it's for axion-like particles is the most common case, like, but anything where you're sensitive to like charge, right?
I'm sorry, I don't understand this interaction. How are we getting this with huge charges?
So what?
How are we getting this kind of interaction with large charges?
So there's 82 protons in, or there's 82 protons in here. So 82 times 3 valence quarks. Each quark can radiate a photon, so the cross section becomes very large when you sum over all possibilities.
But this photon-photon coupling here.
Oh, that's just through the loop.
Oh, okay, sure.
Yeah, so the full diagram is this guy, right? And you have a top loop,
Sure.
Right? Yeah. Question?
No.
All right. I can repeat it.
Yeah, where the bounds on the elliptic surface for its place of jets, your shows?
I wasn't gonna I don't, so there's no, I looked for bounds of displaced jets cast into sims, and I couldn't find this bound. But I think people are making it like right now. So, I mean, there's actually a few nice displaced jet analyses, both Atlas and CMS. I couldn't find it cast into sims, but that doesn't mean it doesn't exist. I'm like 100% sure there's one somewhere. It might be a Theris recast. It might be a LHC, but for sure in the future, the LHC I think is starting to standardize this. This is actually kind of an open area of research. There's a number of communities looking at this. So you might have heard of the dark showers collaboration, where they're actually trying to simulate like a dark hadronization. So trying to get dark showers and then generate this like these jets where you get like displaced objects or like kind of prompt objects or strange missing energy in the jet. This is like a very active field of research right now because people are getting very excited about the dark sector. Just to pick another one that's become very popular in the past year is these things called SUPs, soft unclustered energy pattern. Before that, people called them soft bombs. And the idea here is that, well, if you have a dark sector, you might as well play around and go full dark on your decays. So you can imagine, again, producing a mediator, for example, like a scalar mediator. And then this can decay through a dark shower. And you can actually get an instanton, right? So an instanton is a complex combination of, let's say, quarks and gluons. So this would be dark quarks and dark gluons. But the important thing from experimental perspective is that this instanton object will kind of be very spherical and like give you a lot of low energy particles. So you can imagine this instanton, and then what happens is that then it eventually decays to standard model particles. But this thing is going to be kind of give you a lot of very low energy standard model particles that are spherical. And in fact, QCD also, right? There's a QCD instanton, and in principle, you can produce this at the LHC. And it's something that's incredibly hard to see. So here's actually kind of the best plot I saw to identify the QCD instanton. So the idea is to build this variable, which is without explaining it, it's the likelihood that this is a sphere. And so instantons are these blue lines. So they're very sphere-like. And backgrounds, like normal quark and gluon decays, like these orange and yellow guys. And they're not sphere-like, they're dijet-like. Yeah?
So if I'm reading this plot correctly, it looks like instantons are about just as likely to be not sphere-like as they are sphere-like, right? If S is likelihood to be sphere-like?
Yeah, S is, no, but they're compared to the background, they're more sphere-like. So these orange and yellow are like QCD, soft QCD and hard QCD, so dijet events basically, or soft dijet events. And you see that these are like very large, 10 to the 9th, right? And this is at 10 to the 6th. But then when you look in the region of high sphericity, the ratio is similar, right? So you kind of reduce the background by a factor of 10 to the 5th. It's a log plot with like 17 scales on the plot. So this is not a flat line, right?
Okay.
I mean,
Thanks.
I don't know why people make plots like this, right? Since just as a rule of thumb, like try not to make plots like this. Yeah, question? Oh.
A question on the soups on the last page here. So on the right side, is your S coupling to quarks there, or is that just a black line that you drew?
Yeah, so actually, no, this is a diagram I stole from the original soup paper. This is an S coupling to gluons. So it's a scalar, and it's coupling to gluons through a loop like this. So.
Okay, and your phi here is what?
Phi here is just a dark particle that then couples to standard model. This could be a dark photon. This could be some intermediate dark sector particle that then decays to like a standard model.
So I guess you could do some kind of easy constraint if this phi was somewhat long-lived, right? And-
Correct.
Yeah.
Yeah. So you could imagine something like this, right? But in the case of the soup, this thing would stretch out, right? So you would just get kind of like a circle of long-lived particles.
Mhm. And that would be very distinct, I imagine.
That would be very distinct. If the lifetime though is like very small, it would be almost impossible to identify. Right?
I see. But I guess some kind of plot must, constraint plot must exist for something like this.
Oh yeah, for these, I don't know if they're public, but there are dedicated searches going on right now. One of my good friends is doing one, so there will be results in the next few months for sure on this that are cast in a nice way. Just to be clear, right, there are constraints from the original phenomenology papers, but there's been a lot of back and forth about how to kind of present these in a nice way. And so I would expect to see results in the next few months on these, maybe 6 months scale or less. But this is kind of a very active field of research. There's a lot of people looking at these soup particles these days.
Thank you.
I would just have a question on the last plot that you showed that we shouldn't do plots like this.
Yeah.
So, okay, I understand now why we call this sphericity, but so one thing that bugs me, so on the x-axis, the S, which indices for alpha and beta have we used, or?
Oh,
Yeah, is it important in any way, or,
I mean, no, but I mean, yeah, so fine, this is a tensor. And then you can define, these are in principle 4 vectors, right? So since it's a, so I would just, I think it's just the indices are the normal eta phi momentum like indices. So and then you can just, I don't know how they contract this into a single term. I've forgotten. So yeah.
okay, but then we could use, I don't know, I guess we would get similar results if we would use the thrust, this definition. Where...
Yeah, so sphericity is an extension of thrust. So
okay.
yeah. So thrust is like one of the original observables for this, but sphericity is kind of a generalization to an event.
Okay, thanks.
Okay, so suffice it to say, there's like, you look for sphere-like objects. This is actually for some soup signatures where you have, I guess, 10, 25, or 50 kind of final state dark particles. And what you see is that if you have 10, it's less sphere-like. If you have 25, it's more sphere-like. If you have 50, it's very sphere-like. Top quark decays in the standard model are even more sphere-like. They have actually lots of particles. The top jet will have as many as 100 particles in the final state. Okay, so that was the last kind of craziest model. I wanted to end on something where you really start like pushing the dark sector to something extreme. So now let's recap. So what do you take away from all these lectures? Well, if you want to search for dark matter in an accelerator, what do? Well, the first thing you have to ask yourself is there a portal mediator that couples the standard model to dark matter? And if there's not, you should just go to jail and don't collect $200. If the next thing then, if you do, if yes, though, you can actually start to ask questions. And there's various, I tried to make like a flow diagram. So if you have like a new model and you want to test it out, or you're thinking about experiments, you have to go from the bottom up, you have to see a signature. You can go in reverse. So one way is to ask, well, is my mediator heavy? Well, if it's yes, use the LHC. If it's light, use something else. Does it decay invisibly? Well, if you're at the LHC, you do a MET plus X search. If it decays to dark matter and it's light, you do, and the dark matter coupling is very small, you do a missing momentum search, right? Like LDMX or M cubed or NA64. If the coupling is actually larger, right, then you can actually repurpose a neutrino detector, right, and search for dark matter. If the dark matter is light and its decay is not dominant to dark, or sorry, if the mediator is light and the dark matter is not the dominant decay, right, so the branching ratio of the mediator to dark matter is small, then you can do a visible search. I'll go to that in the next slide. On the LHC side, right, so if the mediator is heavy, and it doesn't decay invisibly, you can ask yourself the question, are the decays long-lived? And if they are long-lived, and the lifetime is long, let's say over a few meters, you can use these displaced experiments like Methuselah or Codex B. Or you could do, if the lifetime is shorter, you can do a long-lived search at the LHC. And if the decays are prompt, we go to the next slide. So at the LHC, if it decays to leptons, I would do the lepton search. If it doesn't, then ask yourself if it decays to something else, right? Something different, then I would search for that something if it decays to something. If it doesn't, and it just decays to quarks, then you do the Dijkman search. And then for light dark matter, right, if your mediator is long-lived, if it's yes, ask if it looks for leptons, and then you can do a displaced dilepton search if it's yes, such as dark quest or heavy photon search. If it doesn't decay to leptons, well, then you have to do a displaced hadronic search, and you can use this with a neutrino detector, NA62, or dark quest. These are kind of similar. NA62 you can also do. And then if your mediator is prompt, you can ask the question, oh, does it decay to leptons again? Where you can do like a prompt dilepton search. If your mediator is prompt and decays to not leptons, then it's actually a little tricky. This is actually kind of hard to find. These would be light quarks. You'd have to think about it at least. So that's kind of a flow chart of what to do. I think I covered all the cases. Here's another way of looking at it. So if you want to remember something, try to remember this diagram. So let me walk you through the diagram. So this is going to be, so I flipped the axes of basically every other diagram in these talks. The y-axis here is dark matter mass. The x-axis here is coupling. And just as a note, right, and it's going from large coupling on the left to small coupling on the right. And this also means that you can go from prompt, so small lifetime on the left, and long lifetime on the right. And so then we can write down all the experiments. Oh, and there's one more. The left here is for visible decay. So let's say your mediator decays visibly. The right is for your mediator decaying invisibly. And again, we're scanning couplings from large coupling to small coupling. This is coupling to the standard model, by the way. And the lifetime here is infinity because it's invisible. And so you can imagine searching for things. So if your dark matter is light and prompt, you can do a prompt beam dump. If it's long-lived, you can do a long-lived beam dump. So this is basically prompt is like a beam dump, you look for decays right after. Long-lived is you look for decays after you put it through a mountain or something. And if it's really long-lived and weakly coupled, you can imagine doing a neutrino detector. If your dark matter is heavy, you can use the LHC. If your dark matter is heavy and long-lived, you can use these experiments like Methuselah or Codex B. And the relic density in some scenarios basically falls along this diagonal here. So small coupling or large coupling, high mass, small coupling, low mass, right? So you kind of, and the strategy is always to get somewhere along this line, right? So this is like one way to remember it. And then on the right here is the invisible searches. And here, you don't vary the coupling as much because you basically just have these invisible strategies. So at the LHC and high mass, you do a MET plus X search. In intermediate masses, you can like Bell or Babar, you can do the monophoton search. And then for light masses, you can do a missing momentum or missing energy search like NA64 or LGMS. And then here's just a table of useful info. I don't know if I'll go through this, but suffice it to say, you can, instead of splitting it by coupling and lifetime and energy, you could try thinking of this in terms of the Lagrangian, right, of the new physics model that you want to search for. And various things play a role. So like on the top, you can think about other ways to observe it, such as direct detection or indirect detection. If it decays to missing energy for these models, right, you can imagine looking for these final states. Oh, and the line is for low energies on the top, high energies on the bottom. So for example, if you want to look for a dark photon and it's low energy, the meteor mass is low, then you look for a missing mass search or missing momentum. If it's heavy, you look for the monojet search. And then, so this is the yellow is the missing energy. The purple is the visible final state. So you can imagine, right, depending on the model, you'll get certain visible final states. So for example, if it's just stay with, if it's a dark photon, right, you want to look for dilepton decays. At low energy, if it's heavy, it can also decay to quarks. So you can get either dileptons or dijets. And then finally, you can write down some sort of benchmark to go after things, right? And so typically that's the relic density. However, there are a lot of exceptions. So like ALPS and scalars, it's hard to get a relic density at low mass, and scalars in particular. However, the dark photon, we have a relic density kind of benchmark across the whole mass range. And I also put heavy neutral lepton on the right here, even though I didn't discuss about it too much. But suffice it to say, you also have bounds there. You also have actually bounds from neutroniless double beta decay, which I didn't get to talk about. And just to kind of put this in perspective, kind of my whole motivation for all of these talks was to be able to explain this chart. So this chart is it's a chart that we put together. Well, mostly a few people put together, and we argued about it. For one person put it together, and we argued about it. And this is for actually a way to explain dark sector searches at snowmass. And so here you can have, there's all sorts of columns. So you can look at this in your own time. But I think this plot is starting to appear in a lot of places. But basically the left here is, so it's split by type of new physics, right? So it's like the previous table. So I split it and I rotated it. And then you can imagine, right, ways to produce it and ways to make plots. So my hope was that you guys understood every single line here. I think there's a slide on every single line in this chart. That was part of my motivation for this talk. And you can imagine looking at the dark matter production, right? So this would be invisible searches here. You can imagine looking at mediator decays. So this is what we call visible searches, right? And then you can imagine looking at a more complicated dark sector structure. So for example, I mentioned yesterday that there's an inelastic dark matter where you make the dark matter unstable and into decay. Here's some discussion about this. So yeah, please stare at this plot when you have time. And so finally, some conclusions. Particle dark matter comes in pairs. A dark matter candidate and something that talks to the standard model. It can quickly become very complicated. You can imagine a very rich dark sector with dark pions, dark vector mesons, dark everything. The type of mediator interaction drives how we interpret it, right? So if you have a vector-like coupling, right, like a dark photon, it's going to give you different benchmarks than a Yukawa-like coupling that you would see in an axion like particle or scalar. the relic bounds tend to underpin how we motivate these, right? You want to have a model that doesn't overclose the universe all the time. But there's a lot of freedom here, and it's a moving target, but it's at least something that helps motivate these searches. And then the other thing is that even though we're looking for dark matter, right, we want to look for invisible. It's important to keep in mind that invisible, visible, and long-lived, make it a separate category, long-lived. Searches all play an important role, right? And it really depends on the type of search that you want to do. But you want to keep all of these final states in mind, and they all are very powerful in different ways. And in the end, it's really just about the mediator and the coupling that tells you what to look for. And then finally, you can make the dark sector almost as rich as you want. There's not so many constraints. And this allows you to be very creative. And you can imagine a broad range of low energy experiments. And I think Sujit's talk is in the afternoon, and he'll talk about kind of crazy things you can do for dark matter searches. All right, so thank you. Oh, take away this plot, and thank you.
No, it's a discussion.
Yeah. So there are a few things for discussion. So one thing I was thinking is we can have a discussion about how to find G-2. But I want to make sure that if you guys have any questions about any of the slides, please ask.
I am interested in the G-2, so I don't want to take too much time away from that. On this Chargino, this type mass splitting where we can evade things, I was just wondering if there was a constraint plot that I missed. How tightly constrained is this search, I guess?
Yeah, so this is the only constraint plot I have in here, and it's this one here. So if you take the LHC bound, these are projections from a theorist. So if you take the LHC bound, it's at the 500 or 600 GeV region.
It's excluded?
Excluded up to that region. This is to motivate 100 TeV. It goes up to like a few TeV.
I see.
Yeah. The couplings are fixed here, right? Because it's a SUSY. Yeah.
Right. Can you explain what you mean by that?
Right, the couplings, so the Chargino coupling to standard model, but the mass splitting is not fixed. You have some freedom there.
But I mean, there should be some other access for the coupling.
But so in SUSY, right, the couplings are fixed to the electroweak scale. That's at least, it's always assumed that. So.
Okay, I see.
I know that the LHC, the whole of the LHC was built for the detection of the Higgs, right? Like
Yeah.
all the detectors and stuff. And how nowadays, like how you imagine or how you think like a 100 TeV machine, and what will be their purpose? Will it be dark matter? And how you do imagine a detector for specifically for dark matter in an accelerator?
Yeah, that's a good question. So the 100 TeV machine, at the moment, there's 4 things they talk about to explain. So dark matter, baryogenesis, electroweak baryogenesis, the Higgs, right? So understanding, and in particular, the Higgs VAV, right? So Higgs coupling. And then SUSY is the other one. I think that's right. And so how does this change things? So actually, I think I have. I have a slide on this. No, well, I do it. It will take even longer to find it. So basically what we learned, it's basically the idea is to build something on what we learned. And so the idea is to make something similar to like CMS or Atlas. But But then the thought is that LHCb has actually been very successful. So the idea is to take the idea for what they want to do for a 100 TV machine. This is the last discussion, is to do kind of like CMS in the center. And then put LHCb here on the sides. And so it's one experiment like this. There are things you can improve in CMS and Atlas to make it better. In particular, they want to make sure that you can do really good displaced object measurement. So, and the strategy here is that you want to instrument the detector with more tracking. So we found that like silicon tracking is really powerful. So the idea is to put even more layers of tracking. So that's basically the idea. For missing energy switches, this doesn't really change things too much. The one thing it does change is that if you have LHCbs on the end, you can basically measure particles almost all the way down to like the collision axis. So, and you know, this would be a very expensive detector, but it would actually be by instrumenting it all the way down, you can actually really reduce the backgrounds a lot in missing energy switches because you can veto things that go into switches. It's not going to be a huge change in sensitivity for like a MET, but if you have very good displace tracking and forward detection, you can actually do really much stronger bounds on like long-lived particles. So you can imagine even like extending this and doing like a phaser experiment. So, right, you can like build it all pieces up, like getting closer and closer to the beam. So.
Just to follow up, how do you get up to 100 TeV? Is it just stronger magnets?
It's a bigger circle and it's stronger magnets. It's some combination. So at the moment, the magnets we have at the LHC are 8 Tesla, and there's a push to make 16 Tesla. The problem is that you have to switch the type of superconducting wire, assuming it's not a warm superconductor. So you have to go to this niobium titanium, and the current ones are something else. I'm blanking. And the thing about it is the current ones, it's the same wire that you use when you make an NMR machine. So it's actually kind of cheap. The new machine, you would have to build your own wire manufacturing company. And you would have to build these at these higher speed fields. There's a possibility that with warm superconductors, you can actually go to make a really high B field magnet. Like instead of 16 Tesla, you could go to like 50. Now the thing is, right, the larger the magnetic field, the smaller the circle you need to make, right? So if you can go to a much higher magnetic field, you can shrink your circle. So if you had like 50 Tesla, right, magnets, and you went, currently we're at 7 Tesla, you could actually increase the beam of the current LHC ring by a factor of 7. Otherwise, you have to make the ring larger, right?
So I guess also the warm superconductors solve the need for helium, right? Which is going to become a problem soon too.
Yeah, helium's an issue, but I never understand how big of an issue this is, right? It's one of these things that people complain about, but I actually never understood whether it was a big issue or not. People don't seem, this is not, like if you go to an FCC meeting where they're talking about 100 TV machines, their concern is not the helium content. We're much more concerned about how are we going to build these wires, right? Because if you look at the cost, right, like 90% of the cost is like building the superconducting wires. Right?
I guess mining the moon is cheap compared to building a 100 TeV machine.
Yeah, exactly.
The highest cost is not the tunnel.
No, the magnets are actually more expensive than the tunnel for 100 TV machine. Tunnel technology has dramatically improved since the LHC tunnel was built in the late 70s, early 80s. Tunnel technology is much better. I mean, the tunnel was built, there are all these tunnels in China and US, everywhere, Italy, right? So tunnel technology is much better and you can do it. There is 100-kilometer limit on the tunnel, just because of the rock. Basically, once you get beyond 100 kilometers, you have to put the ring somewhere under a mountain in the Alps, and that rock is hard, and it's very difficult to bore through it, and then it becomes very expensive.
Regarding what you said about the radius of the ring, you can just scale your magnets up, but are you not dominated at some point by synchrotron radiation also? Like, isn't that also true?
Yeah,
Or
it's
you neglect
suppressed by
that?
mass to the fourth relative to electrons, right? So yes, for electrons, it's a problem, right? So the magnets, if we were to build a 100-kilometer ring and for electrons, right? Then the energy we could go up to is not so high, right? A few hundred GeV, because of synchrotron radiation. It's not that we don't have the magnetic technology, it's just the synchrotron radiation will dominate. For protons, it's suppressed by like a huge factor, right? So the mass of the electron over the mass of the proton to the fourth. So the energy when it becomes a problem is much, much higher. And like just to even get you excited or not, you can imagine you don't need to make a circle anymore if you have a proton ring. So you can imagine making a ring that looks like this, and you can imagine putting it like if there's a mountain here, you can actually have it go around the mountain. So there are people who discuss this, but there's a large contingency of people who like electron-positron colliders, and so they want to make it a circle so that they can minimize the radiation.
Yeah, before thinking about dark instantons, are there any experimental evidences for QCD instantons or instanton fluids?
Yeah, so there is actually there is some evidence in condensed matter for seeing the QCD instanton. And there's another controversial result in heavy ions where the idea is that, so, all right, for people who don't know, instantons, you have to have, you observe, like, it's a combination of forces. So you have to have like if you observe modification in QCD in a magnetic field, you can look at instanton effects, right? So the idea, or at charged field. So the idea is that if you have two heavy ion atoms colliding, you can build a very strong field. The field strength is huge. And then in that collision, they look for a charge asymmetry of the particles that are produced. And that would be an instanton interaction, right? QCD instanton. And there are these various measurements called the chiral magnetic wave, you might be familiar with, where they actually look for QCD instantons. And this was a big topic the past like 5 years, right? So STAR came out with a result claiming the chiral magnetic wave, as did CMS. But then what they found is that there was kind of selection biases because you have to, at these colliders, you can only see charged particles above a threshold. And if you started lowering the threshold, the charge asymmetry started to disappear. And so it's become a huge debate as to whether they've seen the QCD instanton. There is an observation in condensed matter. I've forgotten exactly how it's done. It's some material measuring some current. I don't know the details. But at least the claim is that it has been observed in condensed matter. But certainly the observation in like heavy ion collisions, first people believed it, and basically over the past 3-4 years, people have decided that this looks like some sort of biased selection, and they don't believe it now. And there are a number of studies very recently of people trying to look for it in proton-proton collisions, and nothing is convincing. Like you can look at this plot and it seems very difficult, right? To actually select these events, right? This is assuming you could select events like this. These are events that we throw out. These are typically the events that don't pass the trigger. They're low energy. It's like, imagine a sphere of low energy particles. This is what we typically think of as like trash at the LHC. Most collisions look like this, right? And so now you need to look for a very small deviation on top of these low energy particles. So it's like, it's one of these things that, you know, seems almost impossible. It might happen. Certainly, a lot of us are thinking about it. I mean, it's kind of an active discussion topic. Soups, on the other hand, just to go back here, you can actually do a mono soup. And that's actually where people are going now. So you can imagine taking the same diagram, right, like a scalar, and you can have a gluon, and then you can have a jet. So, and then you can have your soup on the other end. So what you can do is you can reconstruct your soup, and then you can require a jet like mono jet, and you can do mono soup. So yeah, like a mono soup. And this is actually what people are doing these days, is to look for a boosted instanton, right, that has a jet requirement. Okay, other questions? All right,
Maybe I can ask you.
what?
So you said that you're on CMS. Can you tell us on which experiments you're on beyond CMS?
Yeah,
ArcQuest, what?
yeah, so I'm on, yeah, CMS, I'm on DarkQuest, and then I'm kind of on Lego these days. So, and then, I'm actually, M cubed, right, so muon missing momentum. I'm trying to merge it with DarkQuest, so I'm in like a discussion now. So if M cubed doesn't exist, there's not really an experiment yet, but given G-2, we're trying to build it very quickly. So, yeah, but that's fine.
G-2.
Yeah. What?
You want to talk about G-2?
I was gonna talk, yeah, I can, we still have
I would
time.
like to hear G-2.
All right. All right, so this was supposed to be a more discussion topic. So you guys know about G-2. I think everybody reads the newspaper. So how do you get them? So what G-2 is doing is this interaction, right? So muon interacting with a photon. And the interesting thing is that we see a modification, and that modification will come at loop level, right? And so these are all kind of the normal ways G-2 would, or the muon G-2 would be affected, right? QED, weak, some sort of Higgs coupling, right? This is another Higgs coupling. And the way you measure it is you measure this oscillation frequency with, you fit this function. And that, I mean, this hides a huge amount of work. And here's the result. So the conventional standard model prediction is here, right? The Fermilab result is here. The Brookhaven result was there. The average is here. There's this BMW result that people like to, every time you show a plot like this, somebody says, oh, we don't care because we believe the BMW result. I still think it's interesting, and the BMW result. I mean, some people, that's another discussion to have at dinners, whether you believe the BMW result. Yeah, what?
What is
BMW, so there's basically two ways to calculate the G-2. One is based on electron-positron data, and then extrapolating to get G-2. So some combination of a theoretical calculation and data. The other way is with lattice QCD. And the day this result came out, BMW came out with stands for some group. I don't know.
the Budapest versus Bucharest?
Okay, so they came out with the result for this, which was this, like their prediction was an error bar of similar size to this, but like shifted over here. In which case it would agree, it would be in like 2 sigma agreement of the best fit. So then the question is, how do you explain it? So I put 2 diagrams here. So I wanted to open this to discussion if people had any ideas. So the simplest way that people are trying to explain it is they add like a new mediator. And the kind of 2 ways that people have proposed are like a vector mediator well, there's a million ways to people are proposed, right? Sorry, the kind of two semi-conventional ways. I think this is, I looked at your paper, I wanted to make sure I had all of the ones. I mean, Yuri just wrote a paper on this, so. And so you can put like a vector mediator here that couples to muons. Or you can imagine a scalar mediator and you have a Yukawa coupling. So the muon coupling will be enhanced, right, relative to the other couplings. And these are two ways to do it. And this would give you a modification in your coupling. And you can actually extrapolate what the value of this coupling is. Maybe. So it's something like this, right? So it's couplings of 10 to the minus, this is like an epsilon. So it's 10 to the minus 3, 10 to the minus 4, right? The bounds I was showing for dark photons were typically 10 to the minus 4, 10 to the minus 5, they're much better. So it's actually a very large coupling, but you can play all sorts of tricks to avoid bounds, right? So, so you can imagine like a mediator that avoids bounds. So imagine you can have a mediator that just couples to muons, right? So I wanted to open this discussion if people had ideas, yeah?
I mean, you almost need it. I mean, you need it to couple only to muons, right? I mean, otherwise your electron magnetic moment will be screwed.
Yes, yeah, so the electron, yeah, if it couples to electrons, it's excluded. But the G-2 for electrons, in fact, the G-2 for electrons, if you have a heavy vector mediator, it's mass suppressed heavily. So the electron G-2 is not heavily influenced by this, even though it's way more precise. As long as this is heavy enough, it's not a problem. So, yeah, question?
Mine's really quick. Has the tau G-2 been measured? Sorry.
No, but that would be cool. Like, I mean, we measured all the tau interactions, and you can calculate a G-2 from that, and it's 1%. It's pretty good actually. But yeah, that would be something. Going after tau interactions is something that people are talking about a lot. So,
These muons here, are these non-relativistic particles in this experiment?
they're relativistic.
They're still relativistic. So
Yeah.
Okay. Yeah, because I was thinking perhaps there are non-relativistic effects, so long-range interactions between these muons. Somehow not forming really a bound state, but let's say a threshold state, which then extends like or.
So yeah, I mean, there are standard model threshold effects when you do the calculation, but I don't think they're super large. So, all right. Oh yeah, and then you can also, so what you can do then is you can take all right. So do you guys have any idea how to search for this? Like in the minimal case? So let's say you have something that just couples to muons, right? How would you search for it? Any idea?
Muon collider.
Yeah. So that would be, that's actually that's the way what people are thinking. So the idea would be to have a muon beam, and if it's low enough mass, right, you can do a muon on the target, right? And so you can imagine that radiating off like your meson, or sorry, not meson, boson. So you can imagine having a dark photon or a scalar, right? If it's a dark photon, I think almost has to decay invisibly. It can decay visibly, right? So this can either couple to muons, right? Or it can couple to dark matter, or you can also add neutrinos, and it still fits your constraints. Yeah?
But like CMS don't have any constraints about this.
No.
So you can see the decays of 2 moles, like 2 moles.
So the problem with CMS is that these couplings, CMS is good at couplings that are large, right? But this coupling is already at this level, right? This 10 to the minus 3-ish level. And so CMS's bounds are typically, if you plot, if you look at the coupling, if you remember from the talks, there's like coupling of 10 to the minus 2 is about as low as we can go. So CMS bounds are like up here, right? So, but it's good if you have a more complex dark sector, you could imagine like dark pion decay to this dark photon that just couples to muons. So you could still use like LHC for this, but it has to be something more complicated. So,
Do you mind if I say something?
yeah, go ahead, go ahead.
Since you said that you looked at my papers.
Yeah, I did.
So if you looked at an older paper though, so there, I think, so it's fine, or you have this super simple thing where you only put one mediator. There's another class of models, which is unlike the one, the plots that you showed, you get a chiral flip on the internal line, so you need two new guys. Then the mediators will be very heavy, the 50. So then the CMS is very relevant because it would have to have electric charges. You need a Higgs insertion somewhere.
Yeah.
But this is
That's
not
not
the
in that
story
paper,
you're
yeah.
going after here.
Well, no, it's, I was going after the simplest one, right? But there's like a, yeah. I mean, I wanted to see, I mean, you guys can ask questions. This is a discussion session, so, yeah.
So with this,
Isn't LHC quite close to excluding electron universality as well? So that gives some evidence that there could be something funky going on.
Yeah, so this, maybe, Yuri, do you want to answer that? You're like walking into, Yuri can answer these questions better than me.
I'm hijacking it.
It's fine. It's a discussion session.
Yeah, so this is, so I think you're asking two questions. One is, you can ask with electron flavor universality, which is this as a, you have this, I think it was mentioned somewhere. So you have B to S.
Yeah, B to S, yeah. T to S, that one.
Over EE. So this ratio is seen to be maybe deviating from what you would expect in the standard model, which is 1. No? So the probability for those transitions should be 1. So if you say that it's due to a mediator, which is light, so less than a GeV, this would be this region here. There's some assumption about the couplings, and you can vary those, and you see that the plots are pretty much the same. Is excluded by an order of magnitude. So that's for a light mediator. The story is different if it's heavy. So this thing can be as heavy as 30, 40 dV, is X here. And then there are no bounds, and 100 dV guy would also have problems excluding. So that's whether that is excluded or not, unfortunately not. I mean, it's not even maybe probable.
Question over there?
no, you go.
Can you maybe get back to the slide where you had like a vector mediator and a scalar mediator? Maybe one slide before for the G minus. Oh yeah, okay, good. So, okay, now I understand like this, that there are two simple explanations, but the thing is, isn't the scalar like chirality flipping while the vector is like keeping the chiralities, in the sense like you have the nu L, and here on the right nu L. And how does this affect the search? And the second thing, wasn't the G minus theta factor next to this chirality flipping sigma mu? When you like do this Gordon identity, then you get those two Coulomb factors, if I remember correctly. It was connected to a chirality flipping operator, no? So yeah, my question is why then to look at the left explanation?
Look at this guy?
Yeah, if it's chirality preserving.
So the chirality flip comes from the mu line. So if you do, I mean, like formally you would have a derivative and you trade it from S to. Doesn't matter.
Yeah.
So this, let's say you start with a left-handed muon, becomes left-handed, goes through, it's left-handed, and somewhere you have a mass insertion. So you usually would write a cross. Here you go from left to right. This is the right to left, and you again across. So it's the same, it's just that you're right, no? Here you would have a left to right, but this is not. That's not where you get the dimension 5. No? Yeah. Yeah, something.
No, just that because they're massive. So I just said because they're because they are massive.
Other questions? So the other question, so to bring this back to something more experimental, right? So the idea in like a simplest model, right, where you have a light mediator, right? You can imagine then looking for these kinds of decays. So you could think about something that looks invisible, right, and something that looks visible. And in fact, you could actually, with this guy, actually with both of these, you can imagine a bunch of kind of interesting final states. So you can imagine muon to muon to muon, right? A trimuon final state. It turns out the bounds on this are really loose. Nobody's actually, the last bound apparently is from the 70s. So if you want to, I don't know who's writing this paper, but the bounds are very loose. I mean, Yanni Khan is writing this paper. So if you want to talk to him, he's writing this paper. But the bounds are very loose. So this is actually a search that we might do in the next few months. But you can also imagine, right, doing a missing energy search, right, with the decays invisibly. Or you can imagine a muon and a photon or a dielectron final state. And it turns out the bounds are not so bad for those, right? So these would be kind of simple experiments I was thinking about. And this is kind of why I'm trying to get this M-cubed experiment inside. This is actually the SpinQuest experiment. So turns out this experiment is small and this experiment is big. So you could take this experiment and put it inside here and it would fit. And then you could actually you can build a muon beam from here and you can actually put the muons in here and then look for like a trimuon or look for a muon invisible.
I mean, so instead of these muon beam experiments, can you repurpose some kind of neutrino detector and look at muon neutrinos and do something like this?
Yeah, so in fact, this has been done. So if there's a coupling to neutrinos in your mediator, you can look for so-called triad events, right, where you have a muon neutrino hits a nucleus and you get a muon neutrino nucleus and 2 muons. And these bounds are incredibly strong. So it turns out that this makes it very difficult to have you can't get the right coupling to explain G-2 and get the exclusions from the trident events. So this gray is the trident event, right? So this is actually assuming, this is a vector model, right? Assuming this neutrino coupling, and then this gray kind of gives you this exclusion on the coupling as a function of mediator mass. And you can see that the G-2 is this Wi-Fi. So it's kind of basically excluded. This is like the best plot where you can maybe avoid the exclusion.
So is this indicating that I can't have my muon neutrino coupled to the mediator?
It's very, very unlikely. So.
I have two questions. I mean, what will be like the role of the future electron positron providers like PLC or something?
Oh yeah.
And what do we like once G-2 reach 5 sigma, if they reach this this is like a ticket to Stockholm, or like you have like this still wait to.
All right, two really good questions.
Yeah.
All right, so let me start with the last one first. So if G-2 hits 5 sigma, do they win the Nobel Prize? My answer is, I don't think the answer is yes. The answer is no until we discover something. If we discover something that was directly came from G-2, so for example, we build like this muon experiment and we see dark matter, then at least one of the Nobel Prize winners will be from G-2. That would be my guess, right? It's that, but it depends on, Nobel Prizes have often gone in very random directions, so there's no guarantee there. So
Okay.
I mean, there's that lighthouse Nobel Prize, right? So, and then the second question is, what's the point of an E plus E minus machine? So the point is not really for new physics. So some people will tell you that you can do kind of light, like dark photon stuff at E plus E minus. The beam intensity is so large that you could potentially probe like a light dark photon through Z. So typically you produce it like on a Z and then you have to shower and you get dark photon. The bounds are okay. These beam dump experiments tend to be much better. Like LDMX, it will be much better than the light dark matter experiment. For the E plus E minus machines for Higgs precision physics are very powerful. So if you remember, like a few lectures ago, I talked about how Higgs couplings can tell us about the scalar Higgs mixing. You can measure Higgs couplings down to 10 to the minus 3 or 10 to the minus 4 in some cases with an E plus E minus machine, and you can't do that at a proton collider. And that will tell you about Higgs coupling, Higgs mixing with other particles. So this will tell you about like if there's a scalar that mixes with the Higgs, which is kind of the conventional scalar model, then it will tell you about like what's the maximum mixing interval between the two.
I think we better stop because the cookies are working. So, Phil, thank you very much. So make sure that you ask more questions. We have one more announcement. So we want to make a t-shirt.
Let's press the, yeah.